All right, so today we're going to be doing day 8 in Advent of Code. The first part of the challenge is that we get a huge list of inputs, and what we have to check is for different letters or numbers, and they can be both uppercase and lowercase and then regular digits. And we have to check, okay, if two letters are aligned in some kind of way, then whatever the distance is in between them, they make a antinode, that's what they call it, at precisely that much distance away on both sides. And if there is 3 antennas, then of course it makes way more antinodes. And I've taken an example that they've given us a bit under here. And so if we look, there's also different letters. So each different letter is a different frequency because these are supposed to be antennas and they give out frequencies. So the zeros are a certain frequency, and if we look, they're all on a line here. And then precisely this distance away, we get this one, and then precisely this distance away, we get this one. So that is how it works. And if we draw all the lines on how it created the antinodes, it's like this. And then here's another one, and then we have A and A here, and then this one connects like this through the A's, and then there's these ones over here, and then let's see what else. So this 0 with these zeros together, and then there should be another one here, but it's outside the map, and then these ones here. So there's a lot of combinations, but essentially what we have to do is to check, okay, for each different frequency, so the zeros and the capital A's, they don't make antinodes. So we don't see one here, for example, on the opposite sides of this. We only get antinodes if 2 of the same frequencies align. So we have to check all of the same frequencies and then check all of the combinations of their distances and, okay, make antinodes. And then we have to count them. And we also have to keep in mind that an antinode can be exactly over a frequency tower. So this is a frequency tower, but there is an antinode here. So if we see these 2 zeros, they would make an antinode right where A is, and then another one right here, but it's outside the map, but the A covers it. So we have to somehow store them in a different place where the current towers don't cover it. So that's what we're going to do. And for part 1, so the first thing that I'm going to do is open the file. I'm going to make a list of all the lines and append all the lines after I've stripped them. I'm going to get the valid antenna characters, which is all the lowercase numbers, all the uppercase numbers, and all the digits. And in Python, you can use .isAlNum, which means is alphanumeric. But I'm just going to be using this so that we can see, okay, clearly what they are. But using .isAlNum would result in the same answer. So the first thing that we do is we collect the antenna positions from the input. So this is the input. We can see there's a lot of different letters, so a lot of different antenna frequencies. So we want to collect all of them. So we iterate through every line, we iterate through every character. We see if every character is in the valid antenna characters, and then we append it, but not just it. We append its X and Y coordinate and whatever the character is. Then we group the antennas by frequency, right? And we do this, I've imported the default dict for this because it makes our lives a little bit easier. And for X, Y, and frequency in antennas, I'm going to put at the key frequency, I'm going to put the X and Y coordinates as a list. So actually we could debug this real quick just to see how this looks. So run this until here. Takes a second to run, and then we're going to be able to see how the dictionary kind of looks like. So if we go over it a couple times, let's see. So we have the frequency map, and then if we look for the frequency map over here, where is it? Frequency map, it's right here, and we can see that, okay, at key number 4, we have these coordinates, 26 and 0, and then 13 and 1, and 20 and 5. So at all of these different frequencies are all of these coordinates that we found it at. So there's a lot of them to work with, but what's important is that, okay, all the frequencies, we keep them together because we only have to compare the frequency 4 with itself, how many ever times it exists. So it exists 3 times. So what's going to happen is there's going to be 3 of them. And then we're going to have to check this one with this one, and then this one with this one, and then the next one with the rest. And since we already checked this with this, we don't have to do it again. But it's going to be 3 arrows. If there was 4 of them, then we would have to do like this as well, and like this as well. So it's a lot more connections. The more frequencies we have, the more towers we have on the same frequency, the more lines we have to draw and things we have to connect. So it gets worse the more we have n squared, depending on how many we have on the same frequency. But if we stop this and we just keep looking through the code, once we've added it to the frequency map, we also want to make a unique antinodes variable, and I've made it into a set because a set that has unique elements only. So if we somehow make the same antinode in the same place twice, we don't want to store it twice. We just want to count it once. And the first thing that I do in this for loop, where I check for all of the items in the frequency map, is we check if there is a frequency that only exists once, then we don't even have to check it because we know it can't make an antinode. But I've tested it without this part here, and it doesn't really make it faster. I mean, it's probably a very small amount where this is the case, but it's still a bit more efficient. And then we iterate through how many positions there are. So as we saw for the number 4, there were 3 different positions. So n will be 3, and it iterates until n, and then it iterates for j in range i plus 1 until n. And we get all of the positions and all the differences. So basically what this does is if we have 4 different, if we have 4 different frequency towers, what it's going to do is going to go in the first one, and it's going to iterate over the other 3. It's going to go in the second one, which is going to iterate through the remaining ones, and it's going to go in the third one, which is also going to iterate through the remaining ones. Because if we did it a different way, imagine that these 4 would all iterate through each other. So this iterates here, iterates here, iterates here. This one also iterates here, here, and here. This one also iterates here, here, and here. And this one here, here, and here. There's a lot of lines that we don't even need to double check because we already know the answer. So there's a lot of wasted time in there. So that's why it is set up like this. And then we get the XY coordinates from the first position and from the second position. And we calculate the difference. So if there is one over here, here's a C and here's another C, we want to know the difference in X and Y steps so that we can know, okay, the third one would be over here, for example. The what did they call it? The antinode would be over there. So we calculate the antinodes by taking the X coordinate minus whatever the step in the X direction is, and then the Y coordinate minus whatever the Y step is. So that is on one side. So if we have these 2 here, then on one side the antinode would be here, and on the other side the antinode would be here. So we have to add it, and then we also have to subtract it from the other step to be able to get it, both antinodes from both sides. So we get both antinodes. Now we check, are they out of bounds? And we do that by checking, okay, if it's in between 0 and the length of the lines. And I say 0 here because we want the X coordinate, and we're also asking for the X coordinate here. And here I say 1 because it's the Y coordinate. And we do the same thing twice because we check for antinode 1 and antinode 2. And if they are not out of bounds, then we add it to the unique antinodes, and also for antinode 2. And that is the entire loop here. So everything will run. It will check all the antinodes, all the combinations, and it will add it to the unique antinodes. Then we just print it. So we just see how many unique antinodes there are. And actually, I can also print the antinodes themselves, so we can see how many there are and what they are, just for fun. I haven't printed it before, but let's see what it is. So here we can see all the antinodes. So there's 1521 at this coordinate, there's an antinode at this coordinate, at this coordinate. So a lot of different coordinates, and they're all unique. And in total, there's 379 of them. Let me remove these. And if we go back to Advent of Code, we also get a lot more examples of how this works. And just the important thing is that a tower can cover an antinode. So here there is another antinode, and we have to keep track of that. And the answer was 379. So we got the correct answer for this one, which is great. And then for part 2, we have the exact problem, but there's one more step in it. 2 more steps in it. So whenever there is a combination, so this T and this T over here, it just continues. So, okay, this is where the first antinode would be on this side, but then it just continues. It just continues at the same distance until it is out of bounds, of course. So any combination of 2 different towers will sort of infinitely make a line of antinodes. And since there's 3 of them here, then we can see there's 3 different lines. So one line here, and then one line that keeps going in this direction. And also, this was a little bit confusing, but what they mean is that the nodes themselves, the towers themselves, become antinodes as well. So once we calculate where all the antinodes are, we have to also add the towers themselves as antinodes because they are on the line of all the antinodes that they create. And then, of course, we have to count all the antinodes and then give the result. So here's another example that they've given us. So largely, it is the exact same code. So if you can see part 1 and part 2, it is the exact same code up until some part lower down. And it starts to be different over here. So here, instead of just checking directly for, let's see, for the antinode 1 and 2 and seeing if it's not out of bounds, what we do is we give it a, okay, 4 direction in -1 and 1. So it means, okay, keep going forward or go backwards. So for each direction of forward and backwards from 2 different towers, we start stepping we start from 1. So we just take 1 normal step because we have the steps in the X direction and the Y direction. So we begin with 1, of course. And then the direction, we multiply it by how many times we're stepping, and then just the step itself in the X direction and in the Y direction. So we have a new X and a new Y, and this will keep running until it is out of bounds. So you can see that this is just while true, and it only breaks when this else statement triggers, and it only triggers if it sees that it's out of bounds. This is the bounds check. So if the X is between 0 and the length of the lines in the X-axis, and then if the Y isn't between 0 and the length of the lines in the Y-axis. And if it is not on the out of bounds, then what we do is unique anti those. We add the X and Y coordinates, of course, and then we do K plus 1. And what this does is next time that we loop through it, so now we're going to be in here again, but when we multiply the direction, so let's say it's -1, we multiply it by 2 now, and the step amount in the X direction and in the Y direction. So if these are the towers, then we go over here, and then we keep going here, keep going down. It's going to keep going until it is out of bounds, and it only breaks when it is out of bounds. Then we have to find all of the antenna positions and add them to the antinode positions as well, to the unique antinodes, because the antennas themselves become antinodes. And one little problem here, if the antenna, if there's only one antenna, then it's never going to create an antinode, so we shouldn't add antennas that are alone and they create no antinodes, because they themselves will not become antinodes. So we only check the ones that exist more than once, and then we add their positions to the unique antinodes. Then we print them, and we get the result. And 1339, and if we look at the result here, that's the same result. So now, to talk a bit about the time complexity of part 1, we have A is equal to number of antennas, F is how many antennas there are per frequency, N is the number of characters in the input file. So if we think of this whole file as N, then as the characters, then N is the whole input file. And reading the file takes O of n, and there's a bunch of different calculations that we do, and we have to keep in mind that for each antenna that exists, there will be more and more and more antinodes because there's just more and more combinations of the antennas that are possible. So it gets worse the more antennas we add. So it becomes f to the power of 2 for each frequency group. So for each frequency, it is f squared, but since we sum it over a divided by f frequencies, then it becomes n plus a times f. So if we assume that this is not too big, then it becomes O to the n. But if in the worst case scenario, it would be that, okay, the input file is just one letter, so a lowercase a. All of these, imagine all of them were lowercase a's. Then there's a lot of combinations to check. So it will be a lot more complex, n plus a squared complexity. The space complexity is not too bad, it's just O of n. But the time complexity can get crazy, especially if a lot of frequencies are the same. But when we ran it in debug, we saw that there's about 4 to 6 maybe in the same frequency, maybe some more in some places, but it's not some crazy amounts like 100. Now, for part 2, it is quite similar. The only difference is that we add a d, which is the average distance between the antennas. And so basically how many steps we will have to take along a line until we hit the edge. So we just add a d to every sort of complexity step. So here we have times d as well. And in the worst case, it will also be d times a squared complexity. But the space complexity remains the same, basically. It just takes a bit more space in the antinodes list, unique antinodes list. So that was the day 8 challenge. If you guys want to join the leaderboard, I will leave the code in the description. And happy holidays, and see you tomorrow.